Good afternoon. This is lecture number 5 on silicon and wide bandgap power devices. I am Anant Agarwal at Ohio State University, and I would like to acknowledge my colleague Dr. Arash Salami in helping me prepare these slides, and also the funding by Office of Naval Research to prepare these slides for this lecture. So, let us get into the next subject of PN diodes or PN junction diodes, also referred to as. In the last lecture, we talked about drift, diffusion, generation, recombination, and in this lecture hopefully we can apply some of those principles to explain the theory of PN junction diodes. So, let us take a PN junction. So, this is a p-type semiconductor in green and n-type semiconductor shown in yellow, and we bring it together, and let us assume that we connect the p to the n with a wire, so the current can flow. So, what is going to happen is we have lot of holes in the p side and we have lot of electrons in the n side. So, by simply theory of diffusion, the electrons will diffuse from right side to the left side, and holes would diffuse from left side to the right side. And in that process, we will have net negative charge on the left side because of the ionized acceptor impurities, and on the right side we will have a lot of donor charges with positive charge. So, there is an electric field set up from right to left, which opposes the diffusion of holes from left to right and electron diffusion from right to left. So, eventually this process will come to a standstill or steady state, and we will left with a built-in electric field like is shown here. And if we integrate this electric field, then we will get the built-in voltage called VBI, which has been shown to be equals to kT over Q, which is, if you remember, 26 milli electron volt at room temperature, times natural log of Na times Nd over Ni square. Na is the doping of the p side, Nd is the doping of the n side. So, you can see from this expression for built-in voltage, as we increase the temperature, we know that Ni will exponentially rise and built-in voltage VBI will reduce. So, nevertheless, if we have a PN junction, we have a built-in voltage and a built-in electric field, and we approach a equilibrium or steady state. So, now you can imagine that we have very little electrons and holes in this region. Now, let us talk about the Gauss's law, which we will be using to determine that electric field, the built-in electric field. So, if we take an arbitrary 3-dimensional surface or object and we look at electric field vectors coming out of that object or going in, and we do a surface integral of that electric field along the surface of that object. So, basically what we are doing is taking a dot product between the electric field vector and the area vector, essentially integrating the vertical electric field component times the area across the whole area, outside area of this object, and that by Gauss's law should be equal to the total charge inside that object divided by epsilon s. Epsilon s is a product of permittivity of free space epsilon s and the dielectric constant of that material inside the object. So, now we can apply this Gauss's law in a simple one dimensional case we have for the p-n junction. We have electric field pointing from right to left, and here is a 3D picture of this p-n junction, where we have given it a dimension L into the plane of this screen, and we are saying that this is depleted up to an dimension x n, that is depletion with x on the n side and depletion with x on the p side. We have a positive charge due to the acceptors, negative charge due to the acceptors, positive charge due to the donors, and electric field is pointing from right to left. Electric field is 0 here, is 0 on these perpendicular faces because we are considering only one dimensional case. So, because of all this charge, the electric field is coming out of this so called pillbox. So, now let us consider this pillbox as our object. And if we integrate the electric field coming out of this pillbox at the junction of the p-n junction, we can say that field is high, and let us call it E max, and that field times the cross sectional area of that side face would be equal to the total charge enclosed by that pillbox, which is Q times the doping of the n side times the volume divided by epsilon s for that semiconductor. And if you put the dimension, the values for area and the volume, basically you can show that the maximum electric field is equal to Q times the doping of the n side times the depletion width on the n side x n divided by the permittivity of that semiconductor. So, that is the maximum field, and as we go towards this edge, the field goes to 0. Similarly, on the p side, we can show that E max is equal to Q n a x p over epsilon s, and E max has to be same value for n side and p side. So, the two quantities are equal, and if you take the area under this triangle, that is the area of the triangle is the built-in voltage VBI, which will be the E max plus x n plus x p divided by 2, since this is a triangle. And we will just call the total depletion width to be x n plus x p. So, now since we know that the built-in voltage is from pure thermodynamics is k T over q log of natural log of N A N D over N I squared, we can equate that to this, and we can calculate the values of E max, x n and x p. So, let us consider the simple case where the doping on the n side is equal to the doping of the p side. So, one can show that E max is Q n d x n over epsilon s equals to Q n a x p divided by epsilon s from previous slide. That means n d times x n equals to n a times x p, and the total W being Xn plus Xp, and now you can show that Xn by using these two equations. You can show Xn would be the total depletion width times Na divided by Na plus Nd, and now you can substitute that in this equation for Xn and Xp, and you can show that built-in voltage, which is the area under this electric field, is this. Now, if Na is equal to Nd, then Xn will be equal to Xp, and this would be W over 2, and you can see that this would be you can make Na equals to Nd and get a simple expression for Vbi, and this charge on the accepted charge on the p side would be equal to the charge on the n side. Now, if we take a one-sided junction, which is very common in power devices, and let us say we dope the p side very heavy, and that heavy doping is indicated by the plus sign here. So, we call this p plus region. Then you can understand as Nd Xn equals to Na Xp, and if Na is very high, Xp would be very small as shown here. Xp would be depletion width on the p side would be much smaller than X of n. The two charges will be equal. Q Nd Xn would be equal to Q Na Xp as shown here, and Xp is now very negligible if if this is really a p plus junction. Then your total W is simply Xn, and you can show from the previous equation in the previous slide that area under this triangle, we can only consider the red area, we can neglect the green area because Xp is negligibly small. Then the area under the red triangle is simply Q Nd Xn square divided by 2 epsilon s, because my maximum electric field is Q Nd Xn over epsilon s. So, that you can calculate the area of the triangle by this dimension times this dimension divided by 2. So, that is a simple equation that tells us that if I equate this to the built-in voltage from the previous equation, which is Kt over Q log natural log of Na Nd over Ni square, we can now start to calculate what the depletion width is and what Nd might be. All right. Now, let us consider the forward biased PN junction. So, what we have done is we have taken a battery or a voltage source, and we have applied positive voltage to the P side, negative voltage to the N side, and this is called the forward voltage. And notice that applied voltage opposes the built-in voltage. So, the net voltage across this junction will be reduced by the applied voltage, right. So, now once we reduce the built-in voltage across this junction, then we can diffuse more electrons from the N side to P and more holes from left to right, and we can now have a current flowing in this loop in a clockwise direction with holes diffusing from P to N and electrons diffusing from NP to P, and this is possible because now we have lowered the built-in voltage by the applied voltage. So, this is called the forward bias diode, and this is where we can flow a current from P to N. And if you look at the detailed physics of it, we can see that basically we are, once we have reduced the built-in barrier voltage, we can now inject holes by diffusion to the N side Once they arrive in the N side, they are going to diffuse into the N side, but now remember we have excess carriers into the N side. So, we have a case where P n is greater than N I squared on the N side. So, that means these holes can now recombine with the electrons, and that recombination process will be decided by the minority carrier lifetime of holes in the N side, that is tau p. And similarly, electrons will be injected on the p side and will diffuse through the p side, and they will recombine with the holes, and this time the recombination lifetime will be tau n. So, we define two lengths, these are called the diffusion length of minority carriers. So, for the N side it will be diffusion of holes. So, this is called the diffusion length for p type, that is holes, equals to square root of the diffusion coefficient times the lifetime. And similarly, for the left side, electron diffusion length is equal to a similar expression. And if you look at the carrier densities, we have injected extra electrons on the p side. So, this extra carrier density is basically the equilibrium carrier concentration, which is in the bulk right here, N I squared over N A is the equilibrium electron concentration in the p type material. And if you multiply by this exponent where V f is the applied forward voltage, then this gives you the excess charge, excess electron charge on the p side. Similarly, excess hole charge on the N side, which is p type. And now you can see that as these carriers diffuse, you set up a carrier gradient for diffusion, and the diffusion, if you apply the diffusion equation, you can show that this is exponentially decreasing due to the recombination, and the recombination is simply given by e to the power x over ln, and remember x values in this coordinate system are negative. So, it is really e to the power minus x over ln, and similarly here e to the power minus x over lp. So, essentially what is happening is you are injecting holes into the N side, and these are excess holes. So, that you have N times p is greater than N I squared. These holes diffuse because of the concentration gradient, and then they recombine as they diffuse, and this sets up a forward bias current that continuously flows through that p n junction, which we had talked about in the previous slide. So, if you look at the current components, we have holes which are drifting by the drift because there is a slight electric field set up here. Then these holes are moved in the depletion region because you have this is filled with holes, and then holes are injected into the N side and they diffuse. And similarly, electrons form a majority carrier drift current, they go through the junction, and now these electrons diffuse and form the electron diffusion current. Since the total current flowing is constant, we can say that diffusion current, electron diffusion current plus the hole drift current is equal to the total current on both sides. So, these two components should add up to the total current all the time. So, if we put all that into equations and solve, we can show that current flowing through the forward bias junction equals to a pre-exponent term called i's of 0 times exponent term e to the power q Vf over kT minus 1, and that expression for I0 simply depends on Ni squared and the diffusion coefficients of holes and electrons and diffusion lengths and doping densities as we had discussed. So, now we get a simple expression for the current flowing through the diode, and if you plot this expression versus voltage Vf on the x axis and current I on the y axis, you see that the current has a knee voltage. Below this knee voltage, current is very small if you plot it on a linear scale, and then the current rises with the voltage. So, this is called the forward biased PN junction, and you can see that this knee voltage would be related to the built-in voltage that we had calculated earlier. And generally for silicon, this is slightly less than the band gap. If you remember, the band gap for silicon is 1.12 electron volts, and typically this knee voltage is around 0.7 volts. For other semiconductors like silicon carbide, where the band gap is 3.25 eV, this knee voltage is of the order of 2.7 volts. All right, now let us discuss if we apply the reverse bias. So, in this case, we have applied the negative voltage on the P side and positive voltage on the N side. So, now the applied electric field by this battery is in the same direction as the built-in electric field that we had discussed earlier. So, the two add together. So, what happens is that the depletion width kind of expands both on N side and P side to now account for external applied voltage, and therefore higher electric field at this junction. So, again what is happening is that now we have expanded the depletion region, and in this depletion region N times P is less than Ni squared. So, basically we have upset the equilibrium in this material. Also, what is happening on the P side is we have small number of electrons, which is NP0, because these are minority carriers. They are diffusing to this depletion boundary, and then there is an electric field set up from right to left, which sweeps these electrons from left to right through this depletion region, and then they go to the N side and become majority carriers. Similarly, holes on the P side approach this boundary by diffusion, and they are swept by the field to the N side. So, then there is a reverse current that flows because of this process, and that is called I0, which we calculated in the previous slide, and the expression is repeated here. But in addition, we have this wide depletion region where N times P is less than Ni squared. So, what is going to happen is that we will get a lot of electron hole pair generation. If you remember from the previous lecture where we talked about Shockley-Reed Hall statistics, we said if P times N is less than Ni squared, we get electron hole pair generation by a hole emission process and electron emission process, and that whole thing is described by Ni over the lifetime tau. This lifetime would be the lifetime of holes in the N side and electrons on the P side. W depletion is basically Xn plus Xp. This whole thing is W depletion, and area is the cross sectional area of that PN junction. So, this is also the leakage current that flows through this diode in the reverse direction, in addition to this I 0 term, which is purely because of diffusion of carriers outside the depleted region. So, now you can see that if we have very low lifetime, that means lot of defects in this material, then this leakage current would be much higher than I 0. Also, if this W depletion is large, then you can have higher leakage current, and W depletion would be large if we reduce the doping of the P and N type. Now, also if this Ni is high, the leakage current would go up, and that is very easy to explain, because as you know, Ni exponentially depends on the temperature. So, if Ni depends on the temperature, as we increase the temperature, Ni goes up and my leakage current goes up. And this is a very, very fundamental fact that we should understand, because we will use it for silicon carbide and wide bandgap devices. I think it is good to explain at this point that both silicon carbide and gallium nitride are wide bandgap materials, and as we had explained in the first lecture, that higher bandgap means Ni is 20 orders of magnitude smaller than silicon. So, Ni in silicon carbide is almost negligible, which means that the leakage current to begin with would be very, very small for comparable lifetime in silicon carbide. And that means now we can increase the temperature to much higher values than what is possible in silicon, because Ni would rise exponentially with temperature, but it is, since it is so low to begin with, it will take much higher temperature to get a substantial leakage current, and that is why the wide bandgap materials are called the high temperature semiconductors, because leakage current is negligible at operating temperatures. So, if we plot that equation, you can see that there is a I 0 term here in the leakage current when we apply negative voltage across the p-n junction, but also there is a leakage current component here that increases with bias, because as we are applying the reverse bias, the depletion width is expanding. That means W depletion is a function of bias, reverse bias, and as W depletion expands, my leakage current goes up. So, this current will have a little bit of slope here as the volume is expanding in the depletion region. And then we come to a point where the current suddenly increases very rapidly. In fact, it increases almost vertically here, and this is called the avalanche current that we will explain next. So, for this lecture, I think it is best to stop here, so we can take up the avalanche breakdown idea in the next lecture. Thank you very much.